Okay, good afternoon. Welcome to the second workshop of MindSpore Challenge Pathology Diagnosis 2021. So I'm Felix Lau from Huawei Hong Kong Research Center. So today we are having the second workshop of this challenge. So last week on Thursday, we already have the first workshop. So if you haven't joined us, don't worry, we already have the video recording. It's already uploaded onto our main website and you can find it on YouTube as well. So let me briefly introduce you again a little bit for the challenge. So in this competition, you are invited to use Huawei MindSpore to build your own AI model for what? For doing pathology diagnosis. So it will help you to ensure privacy, explainable, and high accuracy. So in these competitions, we have limited 30 teams as maximum, and you can form your team with 1 to 3 members. We have workshops, we have pitching, and we have award ceremony. So there is 2 important stages from now on until the end. The first one is you submit your model to our evaluation platform. And later on, if you having the top score in the top team, you will be invited into our pitching stage on October 22nd. So let me show you who we are. So we are the organizers here. So we have Huawei, Hong Kong STP, Anbiping, and Ibingli. So let me briefly introduce you a little bit. So Huawei, we have Huawei Cloud Hong Kong and Huawei Hong Kong Research Center. So Huawei Cloud is a leading cloud service provider, committing to bringing affordable, effective, and reliable cloud and AI services through technological innovation. So Hong Kong Research Center is conducting researches in AI, fundamental theory, chips, microarchitecture, software engineering, trustworthy software, and so on. So we have 250 more researchers in Hong Kong Research Center. We have 2 offices here in Hong Kong, one in Science Park, another one is in Tsim Sha Tsui. So almost half of us are holding a PhD degree here. So if you like to do research and falling within these areas, please feel free to send us your CV. We're always looking for researchers to join us. So for Hong Kong STP, I think most of you know us very well. So Science and Technology Park Corporation is a public corporation set up by the Hong Kong government in 2001 to foster the development and innovation technology in Hong Kong. So also we have 2 other partners to help us on this challenge. They are Guangzhou LBP Medicine, Anbiping, and also Ibingli. So LBP Medicine is formed in 2005. It is the first listed company on the Science and Technology Board of the Shanghai Stock Exchange in the field of pathology diagnosis in China. So they have already 500 registered and record products. They have already covered more than 1,800 medical institutions in China. And it has quite a lot of subsidiaries as well. So Ibingli is one of the subsidiaries. So it's found in 2017. The real-time visual field sharing system of pathology medical image analysis and processing system are already widely used in China. So they are our partner to provide all the data that we need in this competition. So we need to thank them for providing this great amount of data here. So here is the competition timeline. So last Thursday, we already have a workshop here to provide MindSpore, model arts, and teach you how to use our evaluation platform. So after you train your model on using MindSpore on the Huawei Cloud Model Art services, you can submit your model into our evaluation platform. If you miss it, don't worry, you can click the link later on the YouTube to find us. Also, the link is already provided in our main website, mindsporechallenge.com, mindsporechallenge.com. So you can look for the link and find the video over there. So today, we are in the second workshop here. We are going to talk to you a little bit more on image pathology diagnosis, more deeply inside, and also teach you how to get the highest score in the explainable AI section. So remember, in our evaluation, there is two parts of scoring. One part is for accuracy, another part is for explainable AI. So don't miss it for today. And then on 24th will be the registration deadlines. So if you haven't submit your registration, please do it in this week. On Friday, we will cut off. And then on 28th September, we have a briefing session. So in the briefing session, we are going to give you some surprise. Again, 28th September, surprise. So if you can come on site here in the Hong Kong Science Park, we are going to offer you some valuable gifts. It is sponsored by Huawei Cloud Hong Kong, so don't miss it. 28th September, come on site to collect your first gift. So, and then after a few weeks, on October 15, it will be the model submission deadline. So at the time of 23:59:59, we will cut off. So we will take the ranking board at that time on October 15, 23:59:59. By that time, if you are lucky to enter the top 6 team in the scoring board, you will be invited to enter the final pitching on October 22nd. So October 22nd, come back to Hong Kong Science Park for presenting your work. So on that day, you have a chance to briefly discuss and to present your AI model design, your business idea, or any kind of creativity idea in front of the judging panels. So we are having the judging panels from various backgrounds, academia, medical, and also from corporation. So don't miss it and achieve as much as you can for your model score to enter the final pitching round. So finally, on October 26th, the awards will be presented in one of the greatest ceremony in Hong Kong. It is a Huawei Cloud Summit in 2021. So it will be held in Grand Hyatt, Hong Kong. So 2 main days, final pitching, October 22nd. It will be in 17W Indo Square, Hong Kong Science Park. It will be start at 2:30 p.m. And then for the award ceremony, it will be on October 22nd in Grand Hyatt, Hong Kong. So don't miss these 2 days and mark your calendar. And also you have to have very good score in your model and in your pitching. So here is the prizes. For the model score, the maximum, the winner will have 60,000 cash and 12,000 Huawei Cloud credit. For the runner-up, you will have 45,000 cash and 6,000 Huawei Cloud credit. Besides the model score, if you enter the final round, pitching round, you have another prizes. You have it. So for the pitching score, if you score the highest one in front of the judging panel, so you will get a 45,000 cash and 6,000 Huawei Cloud credit as well. For all the participants, if you enter the competitions, if you have a submission on explainable AI, you will have a special prize here. You will get a souvenir up to 900 Hong Kong dollars and also 1,500 Huawei Cloud credit per teams. So entering for the special prize is not quite difficult, so don't miss it. So let me briefly talk about what is the problem very briefly. So what you need to do is to train a MindSpore AI model to identify the locations and classifications of cancer cells in these type of pathological images. So the AI model, it will help our pathologists in medical hospital on diagnosis of peripheral pulmonary diseases. So basically in the CS point of view, it is just a multi-label object detection problem. What you need to do is to look for the cancer cells, location it, put a bounding box over there, and also classify them. So how many classes we have? 4 main classes. So later on, we will talk much more deeply into what are these cells. So today, we are so glad to have Dr. Lawrence Chan, he's the Associate Professor of Department of Health Technology and Informatics from PolyU, and also Dr. Yongxiang Huang, an AI researcher from Huawei Hong Kong Research Center, to help us to present to you, to teach you how to do pathology diagnosis and explainable AI. So before we start, before we invite Professor Lawrence Chan to come out, please scan this QR code. So for the top left corner, it is the official website. It's exactly the same as MindSporeChallenge.com. If you want to join the game, if you haven't found your teammate, you can scan the Discord code. The Discord QR code is a server that we use to communicate with each other. So most of the announcements or discussions or questions, you can raise it in the Discord channel. And then go to our GitHub to get more resources. We have already published some sample code, some materials on the GitHub. And finally, you have to know what is the rule and how to calculate your point. So again, go to the rule books and guidelines to get more information. So is there any questions online and on-site as well? If there's no questions, then I am going to invite Dr. Lawrence Chan to help us to give the first talk on pathology images. All right.
Okay, thank you very much for Felix's introduction, and also thank you very much for your invitation to this talk. Okay, so I'm my great honor to be invited to share with you actually my experience and also my research work, which is related to the pathology. Okay, thank you. Okay, so good afternoon, ladies and gentlemen. So I'm Lawrence Chan from the HTI Department of Hong Kong Polytechnic University. So today's topic is AI image pathology diagnosis, okay, which is the first part of today's training, which is talk about more or less in the pathology part. So before we start, okay, maybe I think there is not too many people here, but I want to know a little bit background. So is that the audience here with the pathology background or with medical background? Raise your hand if you have such background. And also if you have a little bit experience in handling the medical data. Only a little bit is okay. No, okay. So so which means there's I think here is totally with the computing background. Okay. So I think it's nice. Okay, I can introduce myself first. I'm also in computing background. Many years ago, I graduated in Hong Kong U engineering faculty. So at that time, I studied a PhD in AI. At that time, I have no biology, no medical background. And then I joined PolyU 20 years ago as a research fellow. And then later on, I go into the field of medicine, okay, and also working in a lot of digital imaging in medicine. So this very fit today's topic, okay, I would like to talk about. And also I have applied a lot of AI application on this. So what is a pathology? So I know your background, so if I introduce something which is out of your understanding, okay, please let me know. I will say in more layman wording. So pathology diagnosis, okay, within this big category, okay, we can look into the cellular pathology, okay, it's a study of the disease into the organs, because most of the case, if we talk about the cancer biology, okay, so in the cellular level. So how come the cancer? The cancer is a single clone of the cell, just a cell inside the, for example, inside the lung, inside the liver, having the mutation. And that mutation is only happen in one single cell, in one single clone. And then that one single clone, okay, will proliferate and differentiate into many cells. And then this kind of abnormal growth of the cell, we make the tumor. So that's why we make a tumor, and then the abnormal cell, the adjacent normal cell will be under a large pressure and will be sometimes the other organs function, okay, will be impaired. So the cellular pathology, we look into organs, tissue, and also cells. Okay, the cells is the basic unit, okay, basic building blocks inside the cell, inside the organ and also the tissue. Histopathology, or you can say and also the cytopathology. So histo means a block of tissue, okay, this name, and also cytopathology. Cyto means a cell, okay, at the cellular level, okay, are the key diagnostic tests. So in the initial detection and diagnosis of cancer, okay. So nowadays we have a lot of tests, like if you can draw the blood, okay, take the blood, and then we can look into whether it's a cancer cell in our circulation. So it's also one of this kind of tests, okay, we can help to diagnose the cancer and also other disease, and support by modern molecular techniques, okay. So there's a lot of markers to be presented on the surface of the cancer cell. So like the ligand and the receptor, like the lung cancer, non-small cell lung cancer, having the aberrant, having the abnormal activity of the surface receptor on this cancer cell. So this kind of molecular technique, okay, can help to interrogate into this kind of marker. And then the consultant cellular pathologist, okay, is a medical doctor which is a focus, which is specialized in pathology, can provide the information. When they read the microscopic image, they can make the prognosis, means how long, if the patient diagnosed having the cancer, how long they can survive. We call it prognosis. And also help to appropriately direct the therapy. So can it be go to the surgery if you're at the early stage? Okay, can it be go to the target therapy if it's go to the intermediate stage, or late stage we go to the immunotherapy, so on. So this is also helping direct the therapy and post-diagnosis treatment. So after the diagnosis, then what kind of treatment we can prescribe to them. I cannot proceed anymore about this now. Yeah, maybe something stuck here. Okay, thank you. Okay, so the endocervical gland. So it's one of the example, but it's not the focus of this competition. But it's giving you the example for the normal tissue and the normal cell. So on the left is a tissue, but inside the tissue you still can see the individual cells, but it's not that clear. But in general, you can see the overview of the tissue. And on the right-hand side, the cytopathology is looking into particular cellular level. Okay, you can look into the single cell, including what is inside the cell, the cytoplasm, the nucleus, that kind of organelles can be visualized. For the cancerous tissue, you can compare, okay, at the tissue level and the cellular level, we can still find a big difference, okay, in the appearance. Okay, so the histopathology, okay, by definition is the diagnosis of tissue, diagnosis of the disease, okay, at the tissue level, okay, it's a higher level, involving examining the tissue, and even you can see the cell under the microscope. So the histopathologist is a medical doctor responsible for making the tissue diagnosis and help the clinician to manage the patient care. What about at the cellular level? Okay, the cytopathology is the use of a specialist diagnostic technique, examine the individual cell. So you're looking into cell by cell, okay, and extract from the tissue to determine the cause and the nature of the disease. And the cell samples, okay, can be gathered during routine diagnostic tests. For example, bronchoscopy and also the cystoscopy, sorry. So what is the difference between the histopathology and the cytopathology? Okay, can illustrate by this diagram. First of all, for the histo, the tissue are obtained through the biopsy. or the surgical specimen. Okay, so through the surgery, we can take a block of a tissue, and this is at the tissue level. But the cytopathology, the cells can be exfoliated from the epithelial surface. So it's a need to have some device, okay, to collect, like in this competition, the data, okay, the images for those cells, okay, actually from the bronchi, and then go into the lung, okay, to collect their cell sample. They are all epithelial. Epithelial means on the surface of the organs or the tissue, which is the exterior, okay, facing exterior. For example, our lung full of the full of the air, okay, so it's an exterior, okay, exposed to the exterior. So those surface we call the epithelial cells, epithelial surface, and those removed from the organs and the tissue through by the fine needle aspiration. And other things is the tissue is go through a series of process, examined under the microscope, and we can see the detail of the tissue, okay, for the histo. But for the cellular level, the pathologist does not observe the overall architecture of the tissue. Okay, we cannot see the whole thing, okay, but we can see very clear the characteristic of the cell. So like in this competition, the picture, the images we have is actually can look into the cellular level, okay, individual cellular, but not the overall tissue level. So what is next? And the comparison, this is histo. It can relatively longer time to, and also more expensive technique. But for the cellular level, okay, it's a much faster and also triple technique. Okay, so it's that's why it's a widely used technique. And the liquid-based preparation is a kind of a cytology or a cytopathology approach. It's being extensive use for the gynecology and also the non-gynecology specimen. Okay, it's come from the actually come from the women. Okay, and also non-women specimen. And this kind of technique enables the cell to be suspended in a liquid medium. So it provides a medium so that the cell is not only compressed, okay, between the slides. Okay, it's not compressed and allowed to suspend. Okay, it's like a pool of water or inside a glass of water. And the 3D structure of the cell can be maintained. Actually, you can see very clear different layers, okay, different layers, different levels within the cell. And also this technique enables the cell to be suspended in the liquid medium and spread in monolayer, and thus permitting better morphological assessment. Okay, so shape, okay, can be displayed if you have no compression on the cell. It's just suspending, then the lateral shape of the cell can be presented on the slide. And also two widely used technique. Okay, this is for LBP, there's two techniques, the film prep and also the BD sewer path. But it's not too detailed, okay, and not so related, okay, no matter what kind of technique we use. This is an innovative cytological slide preparation technique, a technology in the recent year, and compare with a traditional smear, okay, with just using the swab, okay, and or using some other tools, okay, to have a removal of some cells or tissue, and then just smear it on the surface of the glass. It can preserve the specimen through the preservation solution and go through a series of process. Remove the impurity. Okay, I think it's also important. If you're just doing a smear, there's a lot of impurity, a lot of irrelevant substances, okay, can be found on the slide, and make clear slide under microscope. Okay, so that's why the LBP is superior to the other approach, and the diagnostic accuracy and also the sensitivity are significantly improved. Okay, and you can compare with the traditional smear. Okay, a lot of impurity, and also the organization is not that good, and also the cell are not suspended, and those cells may be on top of it. You cannot see so clear, see through the structure of the cell. But through the suspension, okay, the cell can be individually and can suspend and also having a good enough separation with each other, and they will not stick in the vertical way so that you cannot see. Some cell will not be hidden by the other, will not be hidden by the other. So this is some example of the LBP cytology. Okay, you can see quite clear at the cellular level, the nucleus and also some other organelles inside the cell. And there's the equipment, okay, used for this kind of LBP technique. Okay, so I explain to you one by one. First of all, we collect the specimen, and also through the vibrator, okay, so that the distribution, okay, can be even out, and then it will transfer to different tubes. And there's a gradient centrifuge, okay, so you have different levels of centrifugal force can be applied so that the cell can be separated, and also with different types of the cell can also be separated, and eventually prepare the slide and also staining. Okay, it's also important because some cancer marker, okay, some cancer marker can be presented on the cancer cell after staining. Then those cancer cells will have the color can be distinguished, okay, from one single slide from the other normal cell. Okay, eventually the slide will make like that. So this is a fully automated and also the standardized slide production process to ensure efficient and also stable, high quality slide preparation. So how we collect the sample, okay, through the bronchi brushing process. And this kind of bronchial brushing is used to find the cancer and changes in the cell that may lead to cancer. And it's also used to help diagnose other lung conditions. And we also call it the bronchial brush biopsy. Okay, it's a kind of sample collection process. And this procedure in which the cells are taken from the inside of the airway that lead to the lung. So I will show you in the next slide. There's a tube, okay, a tube-like equipment. Okay, it's a bronchoscope. It's thin, it's a very thin tube-like instrument, and with the light, okay, at in front of it, and also a lens for viewing, so that the pathologist, when they collect the sample, they can the medical doctor, when collect the sample, they can also look into the condition inside and insert through the nose or the mouth, and then into the trachea, bronchi, and eventually to the lung. And a small brush, okay, is trying to remove, okay, it's a brush to remove the cell from the airway, and those cells then can be looked at under a microscope. So this is the picture provided by Felix. Is I think the medical doctor through this equipment, okay, can look into when the tube go into the trachea, bronchi, and also the lung, then the equipment can see every single detail inside the lung, and then there's a small brush can enter, okay, to the lung, and then to remove those cells. And the respiratory epithelium will be on the surface, okay, of the interactive surface, okay, when we brush the surface, which is we call it respiratory epithelium, okay. Epi means the surface, okay, on the surface of the airway, okay. Air, or also call it airway epithelium. The cell on the surface, okay, epithelium. A type of ciliated, okay, columnar epithelium, okay, lining most of the respiratory tract, okay. And also there's a mucosa, okay, sorry, respiratory mucosa, and we preserve, okay, the moisture inside the lung, or keep it moist, okay, and also protect the airway. So there's 4 main types of cell on the lining of this respiratory epithelium. Okay, so different kinds of cell, like the mucous cell, Okay, we can also call it the goblet cell, and also the mucus layer, which is the mucus secreted from the mucous cell. And also there's some cilia, okay, like the hair, and also there's stem cells, okay, which is the having the multiprotein, okay, which can be further differentiate into the basal cells and also the cup cells. So which is inside the 4 major types of the cells you can find. So that's why the brushing is possible to get these 4 types of the cell, okay, on the slide. And then the trachea and the main bronchial and epithelium are covered with the 2 or more layers of the columnar cells. Okay, so most of the cell actually you collect would be the columnar cell. I'm sorry. Okay, the columnar cell, the epithelial cell is this kind of cells. Okay, you will collect about, I can't remember, it's about 70% of the cell on the side. And not all of them, okay, extended to the surface of the epithelium. So this is one of the characteristics of the cancer cell. If it is not exposed, then not extend, okay, there will be a lot of that they will not have the cilia, okay. So, and also is an example of a spatial arrangement that determine the cell differentiation, okay. And normal cell differentiation, okay, can be identified by this characteristic. They are columnar cell, but no cilia, okay. They cannot extend to the surface through the cilia. And in the smaller branches of the bronchus, and the number of the goblet cell and other cilia cell gradually decrease and become more crypt cell, okay, can be found. So it's also another characteristic of the site, okay. And also the ciliated columnar epithelium is easy to form a cluster and also fall off. And the liquid-based slide show a densely stained cell cluster, and the interpretation, okay, is in most of the cases difficult, no matter it's under a microscope by the human interpretation or through the AI recognition. So that's why this competition is meaningful, because of this kind of characteristic. Okay, that's also you need to pay attention. And this is a LBP slide. You can see the cells, okay, nucleus of the cell is quite dark, okay, when comparing with the other part of the cell. And also another slide, okay, showing the LBP slide. And I read the sample data actually from the website. There's a basic classification of the non-small cell lung cancer and the small cell lung cancer. There's a 2 big category, but under the non-small cell lung cancer, we have the squamous cell carcinoma, SCC, and the adenocarcinoma. But there's one more class, okay, which is the one more subtype, which is called the large cell carcinoma, also under the big category of non-small cell lung cancer. Okay, so but this is what you need to pay attention, because when you look into the data, now you can download it, the classification of the lung cancer in the data set of this competition. For the sample number, sample 0001, so you'll find that it's a non-small cell lung cancer, is a label here, but also it's a squamous cell carcinoma. So it's a go to the branch here, okay? It's belong to this big category, and the subtype should be the squamous cell carcinoma. So this is very, very straightforward, okay? The squamous cell carcinoma. But there's another case, okay, 006. We have the non-small cell lung cancer, but the 2 subtype is not, okay? They are not belong to the other 2 subtypes. So in this scenario, so this I want to raise a point, which means that possibly they are the large cell carcinomas. It not belongs to this one. Why we have that kind of data? Because in the clinical practice, this 2 is easy to differentiate. They have a similar characteristic, is easy to visualize. But this one, okay, if the pathologist is not sure, they are not sure they are this particular subtype, but they are sure that they would be the non-small cell lung cancer. They just specify in a broader the wider cast of the definition. Okay, so that's why we have this kind of separation. Okay, this kind of labeling. Okay, in the data set. And this large cell carcinoma, this is my suggestion, is implicitly indicated. Okay, if you find this kind of classification in the label. And also, what is the morphology of the lung cancer cell? So for adenocarcinoma, the nucleus will be very clear, okay, very sharp, okay, in the image. And the nuclear chromatin is the material inside, is also highly enriched and fine granular. You can see a lot of small spot, but highly enriched and slightly and moderated stained. So if we're having particular staining, particularly on the nucleus of the cell, then the staining will be, the color will be very dark, okay? If it's stained by blue, it will be a saturated blue. With the red, you see a lot of red color here. And often has an obvious single large, okay, nucleoli. Okay, what is nucleoli? Is here's a nucleus, and then you will see a big compartment, okay, a small compartment inside the big compartment. Okay, this small compartment is a nucleoli, but different from the spots. They are the chromatin. The spots are the chromatin, and these are relatively big things inside the big nucleus. We call it the nucleoli. Okay, inside the nucleus. So what about the squamous cell carcinoma? So it's pheomorphic, okay, which means that the heterogeneous shape. So which means that inside those cancer cells, they have the nucleus is not, okay, is not regular shape. When you compare with the previous one, the adenocarcinoma, so most of them actually spherical, and some of them elliptical. But this kind of shape is much more irregular, the nucleus, in terms of the shape. And having irregular chromatin, the chromatin inside is also irregular and also permanent, and also multiple nucleoli can be found. Okay, a lot of nucleoli can be found inside the cell with an inconsistent size and also the shape. Some nucleoli inside the nucleus is large, some are small. Okay, so it's one of the characteristics. You can differentiate between these two major subtypes. And also another big category, which is a small cell lung cancer. We have the round and spindle-shaped cell. Sometimes it's a spindle shape, sometimes it's a round, okay? And a deeply stained. So if you have the staining to a particular cancer marker, okay, will be very deep staining. And having irregular nuclear membrane, so the nucleus having a very irregular membrane and also small nucleoli, okay, when comparing with the previous two subtypes of non-small cell lung cancer. And also having a lot of small dots. They are salt and pepper nuclear chromatin. So it's a material inside the nucleus. We call it chromatin, okay? A lot of dots, okay, you can find, but this slide may not show very clear about those dots, okay? But when you adjust the contrast, you can see a little bit about that. So why we need the AI? Because one of the advantage we can take is trying to solve the serious shortage problem of the cytopathologists in China, particularly, because we have a lot of sample, and also we don't have very systematic training for those pathologists. Some good hospital, they may have a very good pathologist, but for those, okay, it's not that high profile, then the training will be poor. And the emergence of the whole slide digital scanner, we can see a lot of cells covering a lot of cells, and the advance of the deep learning algorithm in AI to make the visualization of the cytology AI possible. And there's also many AI products in the market, okay, which is talking about the cervical cytology. Okay, cervical means the one of the organ of the women called cervix. Okay, cervical cytology have been launched in the market, but non-cervical cytology AI is still emerging. So that's why we have this competition, because the market still don't have that kind of AI product. And also two main AI application scenario. We have to screen the negative, okay? This to trying to spare the pathology workload. their workload is very heavy. They look into a lot of slides, and then they need to zoom in to every single cell, okay, to check, okay, whether there's any cancer cell. But there's a negative. That's easy, okay. You can screen all the cell if they're low alarm by the computer program. There's no abnormality, then we can confirm the low negative. There's all negative cases, and also can help assist to judge the positive, to present the cancer cell, to sort them, and also with the risk index, okay, to tell, okay, like this, including the staining, including the shape of the cell, including the shape of the nucleus and the chromatin appearance, all these things. We can calculate a risk score, okay, so that can give the pathologist some opinion, okay, to suggest whether this case is a cancer or not. And the pathologist can conduct a comprehensive analysis based on the AI suggestion and write the pathology report. Okay, so I think that's all. So if you have any question, okay, you can let me know. Okay, thank you very much.
If we go back to the cells images, for example, squamous cell and even before adenoma, yes. So you have just, yes, you're right here. So you have talked about all of these cells, they are adenocarcinoma, but is it each of them or in the whole pictures, all of them, they are carcinoma? Or,
so because they are actually through the process, the whole batch of the cell will be, if it is the tumor site, then the whole batch of the cancer cell, okay, can be removed. Okay, so at least they will stick together. Particularly for the columnar cell. Columnar cell is highly enriched in the endothelium, so they are stick together. So it's very likely they will form this kind of cluster on the film. Yeah.
so which means on the other side of the picture, let's say these parts, so these cells, if it is not bounded, let's say if it is not labeled, so these are not the adenocarcinoma cells, right?
I can say that this is maybe different types of the cell on the endothelium. So and the other type of cell, they may be normal. Okay, so but for those identified with this kind of characteristic, very likely to be cancer cell, and they will form cluster. Okay, if they belongs to the columnar cell, this kind of cell type. Yeah.
So also within our data sets provided by LBP Medicines, if the pictures without any bounding boxes, so those pictures will be the normal cells as well. So which means as some slides, some of the cells, they are carcinomas and some of them, they are not carcinoma. Yeah. Okay. Great. So, do we have any questions online as well? All right. So on site, great. So if there is no questions here, so we will have a break here. So around 3:30, we will come back here online. And now you can take a cup of coffee, go to the washroom. So we come back and see you again at 3:30. Thank you.
Okay, thank you. So I guess you can hear my voice now. And sorry for the inconvenience. I guess the audio system also require interpretability. And thank you for Dr. Lawrence's introduction to pathology images. I will continue to give you a brief tutorial on explainable pathology AI. I'm Yongqiang Huang from Distributed Data Lab in Huawei, Hong Kong Research Center. So in the first part, we'll give you an introduction to the background of XAI. So here is a basic pipeline in pathological diagnosis using deep learning-based diagnostic models. You can see that after we perform sampling on tissue and imaging digitalization using the electronic microscope to get the pathology images. We will develop a diagnostic model to decide whether this slide or image is malignant or benign. And along with this diagnostic decision, we would like to provide the doctors with some reference evidence to explain this decision. For example, we will localize the, the detailed evidence that supports this decision. And this kind of deep learning-based diagnostic model has been evaluated in a lot of modalities, including histopathology for breast cancer and cytopathology for cervical cancer. But most of these models were trying to improve their accuracy compared to other methods. And not quite a lot of works focus on their how trustable or interpretable of these models, and they are very important to the clinical deployment. Here we also show a table that how these AI techniques can actually accelerate the efficiency and accuracy in clinics. You can see that without the assistance of this deep learning diagnostic model, pathologists in a study, a pathology have an average accuracy of 83% to find out the cancer metastasis for breast cancer diagnosis. And with the assistance of deep learning models, it can improve about 8%, which means that we can reduce about 8% misdiagnosis rate. And also the efficient speed is also get a significant improvement from about 2 minutes to 1 minute. It also make the doctors to feel easier to make the diagnostic decision. And so besides AI's application in pathology diagnosis, we also know that there are AI has empowered a lot of real-world applications in many fields, including healthcare, smart city, auto drive, and fintech. Take the left figures as an example. In the past, if the government want to detect the flaws or the problematic components in these cables, we require humans to climb up there and then check one by one, which is very extremely exhausting. And with the computer vision model, we can detect these problematic components by using like CNNs or other detection models. And also they are also have deep learning models has also empowered lots of possibilities in auto drive. And in this task, they all require both accuracy and reliability. It doesn't like a simple natural image classification. We can accept some error, but in these cases, errors is very high cost and we may not bear it. So explainable and trustable AI are demanding in these applications. What is explainable AI? We can see in this figure, traditionally, we trained a model with some input data and labels, and on the new data, we predict for the new data and then tell the user the results should be some kind of class or other type of result. But we don't know why, because the model is a black box model. We only know is numerical value of the neural networks or other kinds of or any kind of other deep models. But we cannot explicitly know how the model made this decision and whether we should trust it. And with the assistance of explanation tool, besides this prediction result, we also start to understand how does the trained model make prediction. Okay, so sorry for the unstable connection. So I will review here again. So as we spoke just now, as these applications, they all require high reliability when applying AI. So explainable and trustable AI are demanding in these applications, including healthcare, smart city, auto drive, fintech, especially in finance domain. If we want to decide whether to accept the low application for users, if we use the AI model to predict the risk of the low, we need to provide the concrete explanation for this low decision. And also in the popular quantitative trading, if we use AI model or other machine learning model, we may also require the model to be interpretable for users, as they are not experts in deep learning. So overall, so what is explainable AI? As we can see in this figure, traditionally, a deep learning model will be trained on input data and some labels. Then we can make prediction for some for new coming data. Then we tell the prediction result to users. But here we don't know why the model will make this decision, because this is a black box models like neural network. We only can observe the numerical value of this model, but we cannot explicitly to know how this model can make such a decision. So we cannot decide whether to trust it or not in some cases, when this domain is not our expertise, for example, pathology. So with the assistance of explanation tool, beyond the prediction result, we will also provide some explanation which can help us to understand how does the traded model make predictions. This is what we termed as global interpretability, because it can explain the model's behavior for different type of data. For example, what type of feature does this model think it is important, or what is the decision logic of this model? Secondly, it will also help us to understand why did the model make a certain prediction for an instance. For example, in this challenge, we will give you some unseen image during texting, and you need to decide whether this image contains some cancerous cell and where is it, and using a bounding box. But after developing the explanation module, the output of this explanation module will show the detailed evidence, specifically the mask that highlighting the cancer cells, the contours of these cancer cells that can map the pathologist's understanding. So with this explanation output, we can better decide whether to trust the model's decision or not. Because we know that deep learning model is limited, especially when it is trained on limited data. So it is very possible that we the model will see some data that out of its distribution during training. So it means that it can make some mistakes that we don't want, and when it is okay for it to make some mistake for some new data, but we need to know we need to know when it will goes wrong, and when we are alarmed, we can make human intervention. So deep learning can be tricky, so we need explainable AI. So we can also see that XAI is also blooming in industry. For example, during the DARPA's David Gunning, they has a XAI project initiated in 2017, and also in China, XAI is included in new generation artificial intelligence development plans. Also, in UK, XAI is included in AI white paper. We also have some detailed rules when we deploying AI in finance domain, and in finance domain, this AI model are all required to provide some explainable outputs. So in academia, we can also see that research on XAI is also a blooming topic in recent years. We can see that in clinical deployment, as we have mentioned before, the black box nature of deep learning has restricted its application to interpret the deep learning model using data in terms of data. For example, what kinds of features in data are important for the model to make decision. And in knowledge aware XAI, we will incorporate human knowledge to give the explanation in terms of human knowledge, like a knowledge graph or concept. And in this challenge, we may focus on local methods here, because in our task, we need you to explain the model's decision on given a set of pathology images. So we need you to output some kinds of saliency map to highlight the evidence that's supporting the detection result. On the right-hand side, I list some detailed methods for the left taxonomy. For local explanation, the very early method, and a classic one, is called align. It is a linear surrogate to for the deep learning models. For example, we are given a concrete instance that we want to explain how our trained deep model will predict, and we will perform some small perturbation on this small instance. For example, we will add some Gaussian noise to this input instance, and we will feed this perturbate examples into our trained neural networks and derive its corresponding outputs. And combined with this perturbate instances and predicted labels, we get a new data set for this concrete instance. And then we use a linear model to fit this new generated data set. And this fit model is a straightforward linear model. So we can use this linear model to explain how the decision is made by the deep learning model on this concrete instance. This is the basic idea of line. And for the computer vision task, the instance is an image. And if we want to perform perturbation on this image, normally we will split this image into a lot of super pixels, and each super pixel can be viewed as a one dimension of a feature vector. So we can still use line to get the saliency map here. And the second type is maybe more popular and more familiar to you. It is a propagation and gradient space method. And most popular one can be GradCAN and guided backprop, and integrated gradient is developed based on GradCAN, but if it's the limitation of GradCAN to some extent, and LRP and D-lift is a propagation-based method. And the third type of method is a perturbation-based method. So as we say, it is a perturbation-based method compared to the gradient-based method. This is model agnostic. Because when we use GradCAN, we will need to backpropagate the gradient from its output layer back to some intermediate layer to visualize the activation. But in perturbation-based method, we not require gradient here. So given an image and a trained model, we will just perturb the input image and see how the perturbation affects the output of the model. And if a certain perturbation, for example, if we play a small black mask on the center of an image, a dark image, and this perturbation leads to a significant drop in accuracy, then we may say the central part of this image is very important for the model to make decision. And we use, and based on this simple idea, we will develop a collusion and rise these two kind of method to find out the saliency map for concrete prediction made by the deep model. And we also have some kind of explanation method based on game theory like shape and D-shape. As we have, as our time is limited, I will not talk too detailedly for all kinds of this method. And we also have counterfactual explanation that will show us how can this model make opposite decision. How can we change the input slightly so that the model may make an opposite decision. We also have some model inherent attention, like if we use transformer model or attention-based CNN, we may have some kinds of spatial attention or channel-wise attention to tell us which kind of information for the model to make decision. And belongs this local explanation, global explanation, which tell us, will give us a holistic view for how the model is, how the model make decisions. For example, you may be familiar with the teacher-student model, and the global surrogate has a similar idea. So as I have mentioned before, we will focus on the local methods, and we will introduce it more detailedly. Here's some list of XA application in medical imaging domain. You can see that it has been widely applied in research, from Alzheimer's disease to breast cancer detection to brain tumor detection. If you're interested, you can read this survey on this topic. So let's introduce more detailedly on the local methods for interpreted computer vision models. So formally, saliency map is used to show the important regions on an image that affects the model's decision. So we can categorize this saliency-based method into two categories. The first one is model dependent, as we have mentioned before, guided backprop and GradCAN and integrity gradient. And the second part is model agnostic. And in this slide, we show some result from the GradCAN paper. We can see in this image, we have a dog and a cat, and for the decision that the model predicted as a cat image, when we use GradCAN, it will highlight the region of the cat. And if we predicted this image as a dog image and use GradCAN to perform a computation to derive this saliency map, we can see that it will highlight the head of this dog. And so literally, when we apply this method to pathology image, the formulation is is almost the same. In guided backpropagation, it assumes that the score function of this image that tell us the class score of for this input image can be estimated using a linear model. I is the input image, W is the weight, and B is the bias. And if we have this assumption, so we can estimate W using the derivative of the score function with respect to the image. So this can be implemented using gradient backpropagation. But in this method, it is called guided because it will stop the negative gradient flows during backpropagation, because we only want to know what is the gradient flow that affects this class prediction. And we also perform some smoothing, like Gaussian smoothing, for this guided backpropagation saliency map, because originally this derivative computation can lead to some sensitive noises. And for GradCAN, the idea is also not so complicated. YC is the class score here, and F is the feature map in a certain layer of the deep neural network, and we will backprop the gradient from the class score back to a detailed feature map, and then we average it over all pixel spatially, and this is used as the importance for a specific layer and a specific channel of a feature map. We have a multiple feature map for an output of a convolution layer or other kinds of layer. So after we know the importance of each feature map, we can just use it as a way to weighty summarize all this feature map. And also we perform ReLU to eliminate those negative values. So this is an example. The left, this column is the pathology images, and this is the result when we use a guided backpropagation to derive the saliency map, and the result are normalized to 0 to 1 range. And this one is the GradCAN saliency map. And this is a simply combination of for the two of them. And and uh, and if we perform thresholding on this saliency map, we will have some binary mask. We derive a binary mask, and this highlighted region is the one values for the binary mask, and we can see that this cell clusters corresponds to the cancerous region, and this is the ground truth. So we can see that when we in this example, we have our trait model will output this cancerous score, and with this explanation method, we can highlight the regions that why if think it is a cancerous image. So belongs guided backprop and GradCan. I will introduce a RISE, another model agnostic explanation method here. So in this this figure, as we can see this figure from the RISE paper, for this input fixed image, this is the explanation result from RISE. It highlights diversely for many fishes here. And if we use GradCan in this problem, as of course I'm not sure. I'm not sure which convolution layer they used for this visualization. Because if you choose different convolution for computing GradCan, we may produce different kinds of result with different accuracy. So let's see how RISE derive this result detailedly. So as we said, RISE is a perturbation-based method that generates attribution maps by sampling on multiple random binary masks. So its idea can be seen here. Sorry. In this column, we have a lot of binary. We have a lot of mask on this image. This dark region means that we will block out the corresponding region in the image, and we perform dot product of this mask and this input image, and we got this perturbed image, and we have this is our trained deep models, and we perform inference on this perturbed image, and then we can get the class probabilities here, and now if we do this perturbation for many time, and we will have a lot of this perturbed images and their corresponding scores. And the key idea is that if we use this class scores as the weight for this mask, for example, if this mask is totally black and is all 0, then this image will be empty. It will lead to a class score of 0, and then we may say it did not highlight the important region of this image, and inversely, if you only mask out the background of this fish and only show this the body of the fish, then the class score is very high, right? So if we perform this random perturbation and then use this class score as the weight for this mask, then the weighted sum of this mask can be viewed as the saliency map for this prediction on this input image. So overall, we can get the saliency map here. This is the idea of RISE, and the advantage of this is that it does not require gradients, but it may also more time consuming as we need to decide how detailed should we perform this perturbation, and yeah, this may influence the algorithm's efficiency. So in the third part, we will show detailedly how can you implement this explanation method with MindSpore, and how we will evaluate this quantitatively. So here we show what explanation method has been that are provided in MindSpore's explainer library. We have gradient, convolution, guided backpropagation, gradient occlusion, and RISE. For the API interface of these explainers, you can see detailedly in this website. And here I will show you. I will share you with the Jupyter notebook. Okay, thank you. So the code is quite straightforward. In this block, we define a CNN, say the net find here, and then we have some given instance. For example, this input, we use some random value here for illustration, and we need to define the target that we want to explain. Suppose we want to explain. Suppose the prediction of this the net is class 1 here, and we use the RISE explainer in the MindSpore explanation library, as we can see here. Okay, so its input parameter is the trade network, and the activation function that we perform the final scoring, and perturbation evaluation. This is defined as 32. As we mentioned before, this number will determine the accuracy and the efficiency of the saliency map. So here we use the default parameters in the RISE class. And this activation function is just this last softmax layer of the net. Then we can simply perform explanation using this function. Its input is an image or multiple images, and we need to define the class of interest that we want to explain. And so if we run this, we can get this saliency map, and its change should be the same as the input image, except for its depth. The input image is an RGB image, has 3 channels, and the saliency map we only have 1 channel with values in range of between 0 to 1. So in this challenge, we require you to develop your own explainer for this pathology detection task. You can start by choosing one existing explainer in MindSpore, and then develop your own explanation algorithm. and but you need to follow these protocols. And we defined a silencing map function with this input and return. Sorry, I'll be back in a moment. Sorry. After you develop your explanation algorithm, you need to wrap it into this silencing map generation function for evaluation. And to quantitatively evaluate your explanation quality, here we set some constraints. So first of all, in this explanation evaluation set, each image will only contain a single type of cancerous cells along with normal cells. So your silencing map should mask out those cancerous cells precisely. And the more precise this silencing map, the more it should match the ground truth that annotated by our experts, which highlights the ground truth cancerous cells. So you can view this as a segmentation task, and your silencing map should give the accurate segmentation on these cancerous cells or clusters. And so we use the AUC between this generated silencing map and okay, sorry for the unstable connection. And I guess this is the final final loss. Okay. We have the explanation evaluation set, which only contain all images that, and each image in this evaluation set will only contain a single type of cancerous cells along with normal cells. And so, this explanation score is measured by the mean AUC of your generated silencing map against the ground truth binary mass that annotated by the experts. And the ground truth this ground truth binary mass highlights the cancerous region on this pathology image. So the more precise that your silencing map can capture these cancerous cells or clusters, the better your AUC score will be here. You can view this as a segmentation problem here, actually. This is the ground truth segmentation mask on the cancerous region. And this is the your generated silencing map that also highlighted the cancerous region. And we take the average AUC of your generated silencing map against the ground truth cancerous mask as the final explainable score here. So that's all. Thank you for your listening. And if you have questions, please feel free to ask. I'm so sorry for the lost networks in this section.
So if you have any questions later on, don't worry. You can contact us on Discord. And also you can send us email to support@mindsporechallenge.com. So we are sorry a little bit, so we have a little bit connections problem when Dr. Yongxiang speaking, but don't worry, we will have an edited video later on to post onto our main website. For the slides day as well, so you can find all the slides on our main website later on. So if you have any questions, again, Discord. If you want to join the competitions, register now, and we are closing very soon. And also, we have already distributed 15 teams accounts information to those registrations who have been verified by us. If you do not receive your confirmation, please let us know. So contact us on support@mindsporechallenge.com or on Discord if you do not receive your confirmation. So please come back on September 28th for the contestant briefing. We are having special gifts for you guys who come to attend on site here at Science Park. And also, you can also help us to spread out the message to your friends, to your teammates, and also to your classmates as well. So welcome and thank you, Professor Lawrence Chan today, and also Dr. Yongxiang Huang online to share all this information. Thank you. See you next week. Bye.